in a counterclockwise direction, looking from the bar magnet side. This current produces a north polarity towards the north pole of the magnet and opposes the motion of the magnet, thereby opposing the increase in magnetic flux through the coil. A force is required to move the magnet against this repelling force. The same magnet, when moved away from the stationary coil, causes the magnetic flux through the coil to decrease. A current is induced in the coil which opposes this decrease in flux. The induced current is in a clockwise direction looking from the bar magnet side. This current produces a south polarity towards the north pole of the receding magnet. This south pole attracts the north pole of the bar magnet, thereby resisting the motion of the magnet. When the south pole of the magnet is towards the coil and it is moved towards the coil, a south polarity is induced near the south pole of the magnet. When the same magnet is moved away from the coil, a north polarity is induced near the south pole. In all these experiments, we can also use an open circuit in the place of a closed loop. In this case too, an EMF is induced, but there is no induced current in the coil. The direction of this induced EMF can be found using Lenz's law. Here is an easy way to understand the direction of induced currents and EMF. We have so far taken Lenz's law for granted. Suppose that the induced current is in the direction opposite to the one given in the figure. In that case, the south pole due to the induced current will be near the approaching north pole of the magnet, causing the bar magnet to be attracted towards the coil. A gentle push on the magnet will start the process of motion, and its velocity and kinetic energy will continuously increase without expending any energy. If this is true, we can construct a perpetual motion machine with a suitable arrangement. This violates the law of conservation of energy and hence cannot happen. So, we can conclude that Lenz's law is correct. In all the experiments discussed, a force is required to move the magnet bar either towards or away from the coil. The product of the force and the distance moved gives the work done on the magnet. The work is done by spending some mechanical energy by the person conducting the experiment. The mechanical energy is converted to electrical energy in the coil. The electrical energy is converted into heat energy by heating up the coil, which is dissipated into the atmosphere. From these observations, we can say that the energy is only converted from one form to another, or the energy is conserved. We have studied about induced EMF in a circuit due to the rate of change of magnetic flux through the circuit. This happens due to the relative motion between the coil C1 and the bar magnet. We know that the induced EMF E is equal to minus d phi by dt, where d phi by dt is the time rate of change of the magnetic flux and the minus sign is in accordance with the Lenz's law. Let this be equation 1. Now let us study about induced EMF produced due to the motion of a conductor in a magnetic field. Consider PQRS to be a rectangular metallic loop having a galvanometer G connected between R and S. The part PQ can slide forwards or backwards in between the parts PS and RQ of the loop. Let us now place PQRS in a uniform magnetic field such that its plane is perpendicular to the magnetic field. For a time-independent magnetic field, the magnetic induction B remains constant both in magnitude as well as direction. Let the length of PQ be L and that of RQ be X. Let the conductor PQ move towards the ends SR with a constant velocity V. We observe that the conductor PQ, the direction of the magnetic induction B, and the velocity V of the conductor are mutually perpendicular to each other. We see that the conductor initially is at a distance x from the RS end. As the conductor moves towards the RS end, it is displaced from its original position and its velocity V can be written as dx by dt. Since the plane of the loop is normal, that is, perpendicular to the magnetic field, maximum magnetic flux passes through the loop. This magnetic flux, phi b, passing through the loop is equal to the product of the magnetic induction B and the area A of the enclosed loop. The product of L and X represents the area swept A. Hence, we can now rewrite the magnetic flux phi B as equal to BLX since A equal to LX. As the conductor moves towards the RS end, we see that X is varying and hence the area A enclosed by the loop also changes with the time. Therefore, we see that magnetic flux phi B also changes with time as the magnetic flux depends on the area enclosed. Hence, according to principle of electromagnetic induction, an induced EMF is developed across PQ. This induced EMF, E, is equal to minus d phi b by dt as given by equation 1. Substituting for phi b, we get E is equal to minus d by dt of BLX. As B and L are constant and only X is the variable, we can write E is equal to minus BL into dx by dt. As dx by dt represents the velocity V of the conductor PQ, we can write electromotive force E is equal to minus BLV. Let this be equation 2. The induced EMF E is also called the motional EMF in this case. The concept of motional EMF can also be explained by using the Lorenz's force acting on the free charge carriers of conductor PQ. We know that when a charge Q enters perpendicular to a uniform magnetic field of induction B, then the Lorenz's force on the charge FB is equal to QVB. As the conductor moves with a speed v, free electrons in the conductor also moves with speed v in the magnetic field B in addition to the random velocity they have within the metallic conductor PQ. The average magnetic force due to the random velocity is 0. But the average magnetic force on each free electron due to velocity v is Fb equal to QVB, where Q is the charge on the electron equal to minus 1.6 into 10 power minus 19 Coulomb. From Fleming's left-hand rule, we can say that in this situation, the magnetic force on a positive charge moving with velocity v in this magnetic field will be along PQ. In accordance with the same rule, we can see that the force on the electrons Fb will be directed along QP. And we see that the free electrons in the conductor move towards P. As a result of this movement, a negative charge builds up at P and a positive charge appears at Q. An electric field is developed within PQ such that the electric field exerts a force Fe equal to QE on each electron. In electrostatic equilibrium, the force Fe will be equal to Fb, and this build of charge stops. Since Fe becomes equal to Fb, we have QE equal to QVB. Simplifying, we get E equal to Vb. Due to the charge build-up, a potential difference is developed across PQ, which is the induced EMF E. We know that the potential difference E is equal to E into L. Substituting the value for the electric field strength E equal to Vb, we get induced EMF E equal to BLV. Since Lenz's law is obeyed here also, we can write this induced EMF as E equal to minus BLV. This induced EMF E is the motional EMF. Due to the induced EMF, an induced current flows in the closed loop PQRS, and the current can be detected by the galvanometer. This induced current flows along the path QRSP. This equation for the motional EMF derived in this manner is the same as the equation 2 which we derived earlier. Now, consider the case when the conductor PQ is stationary in the magnetic field, but the magnetic field varies with time. That is, its magnitude or direction, or both magnitude and direction are changing with time. Since the conductor is at rest, its velocity v is equal to 0, and as seen earlier, the magnetic force Fb equal to QVB is 0. The moment the magnetic field starts varying, an induced current flows in the loop which can be detected by the galvanometer. Since the magnetic field force Fb is 0, the electrons are forced to move only by the electric field, and hence we conclude that an electric field appears instantaneously. This electric field is produced by the changing magnetic field and is called the induced electric field. This electric field causes an EMF to be developed in the loop, and hence an induced current flows in the loop. From these observations, we can say that just like the moving charges in a conductor can produce magnetic fields and exert a magnetic force on a magnet in its field, a varying magnetic field can also exert a force on stationary charges. So, if we move a bar magnet towards a stationary charge, the charge experiences a force due to the varying magnetic field. This is the fundamental significance of Faraday's discovery. Consider a rectangular conducting loop PQRS